Okay, I'd like to thank the organizers for inviting me to Italy. I'm always pleased to come back to my parents' homelands, but I will speak in English today. Okay, so this work I'm going to present, it's a little bit specialized, but it's dealing with definitely a multi-band system, which I'm happy to see that we had a nice introduction to these materials in Sergei's talk just before so just to give you a little bit of the history behind this material, because some people may not know that, you know, in many cases in physics, discoveries are made through serendipity, through luck. And this is another one of those cases where Hosono-san in Japan and co-workers were trying to do something else. They were actually trying to make some transparent conducting materials, and through changing some chemistry of these materials, particular substitutions of transition metal and nictogen atoms, they discovered a superconductor, which was a phosphide, and it was a 4 Kelvin superconductor. So in 2006 it was reported. Not much attention was paid until 2 years later, when the TC went up by order of magnitude to 20-something Kelvin. And then, you know, the whole world started studying these materials, and within months it went up to 50-something Kelvin, approaching 60 Kelvin. So, but nevertheless, this material is, or this system of materials is quite an interesting system, particularly because of the complexity of this family of materials, which, like the cuprates, has one common element. It has this iron square lattice layer, which is actually a tetrahedral layer. So the iron arsenic or iron nictogen tetrahedron is the key ingredient that's found in all these materials. And if it's not there, we don't find high TC, or high TC in the sense of 50-something Kelvin. And iron is particularly key. If you replace it with cobalt at 100% substitution, or nickel or something else, we don't get the same system. It's quite a peculiar system, and it's not known to this day why iron is the special key ingredient. Nevertheless, this system is a beautiful system for experimentalists to study, particularly people like me that like to do some pseudochemistry by doing crystal growth and playing around with perturbations of the crystal structure via substitution and other parameters, because we really span the entire periodic table with this system. We can do all kinds of substitutions, and unlike the cuprates, where if you play with the copper, you kill superconductivity very quickly. But in this case, you actually have to perturb the iron lattice to induce superconductivity in 99% of the cases. And it's nicely shown, in particular in this, for instance, this 1,2,2 compound, where you can substitute barium with potassium, or iron with cobalt, or arsenic with phosphorus, and all three of these types of substitutions in quite different anion or cation positions induce high TC. So it's a very complex system. We don't understand why this happens yet, unfortunately. But it's only been a few years, and experimentally we can use this as a tool to study these systems in great detail. Okay, so because the theme is multi-band, I should of course mention in passing that multi-band also seems to be the key ingredient in these materials to finding superconductivity. And it's consensus in the community is pretty much that we have an S-wave order parameter in the highest TC materials, and also that there's a phase difference between the different bands, such that you have a phase change, a plus-minus phase change between the gaps across these bands. But there's quite a lot of variation. So in particular, it was nicely pointed out in this review article that the gap structure can change quite a bit. So whether you have S-wave with a phase change or some nodal S-wave, as long as the symmetry is the same, you can observe superconductivity, at least it's thought, in many different compounds that have variations in this gap structure. But the symmetry seems to be S-wave in all these cases, except for some lower TC materials where it's thought to be D-wave. And there's some discussion about that, of course. But the structure versus symmetry is a distinction that seems to be very important. Okay. So, Just to note in passing as well that it's been an advertisement for those of you interested in crystals. We grow crystals at the University of Maryland, various compositions, not only of iron pnictides, but also we're studying condo systems, heavy fermion, topological insulators, bismuth-selenide, and so on. Other peculiar materials. We have various methods of crystal growth, including flux growth and high temperature, Joukowsky growth, and so on, even dabble in thin film work and other things. But back to the iron pnictides, I'm going to ask two key questions which kind of motivated this work on the rare earth doped calcium 122 system. The first one is the apparent asymmetry in the phase diagram. So very much like the cuprate phase diagram, where when you whole dope the copper oxides, you get the highest TC materials, upwards of 150 Kelvin. If you electron dope, the TCs, the maximum TCs, are much lower. They're of order 40 Kelvin or so. And it seems to be the case so far in the pnictides as well, in the sense that if you take the 122 material, barium, iron 2, arsenic 2, substitute cobalt, which is thought to de-electron dope, you have a TC maximum of roughly 20, 25 Kelvin, whereas if you hold dope with potassium in the alkali earth position, then you get a TC of 40 Kelvin. And it's also seems to be the case in the 1111 materials. So there's this asymmetry, and the question is there any relation to the cuprates? And more importantly, is there a true asymmetry in this system, in the physics, that dictates the energy scale of superconductivity? The other thing that I'm going to point out, and this is a little bit more detailed, but nevertheless, there's some peculiarity about the phase diagrams in these materials. The first reported in the highest TC materials, these oxypnictides, seem to have a very unique phase diagram where the magnetism, as a function of doping, is abruptly interrupted, and then superconductivity is found. In other words, there seems to be no coexistence, microscopic coexistence, of magnetism and superconductivity. And that will be a key ingredient in what I'm going to talk about. As opposed to the intermetallic systems, where there's a well-established microscopic phase coexistence of magnetism and superconductivity, shown through various probes, NMR and so on. So is this difference between these materials interesting or not, or is it just something that we've found so far and we will find counterexamples of? So what we wanted to do was take a intermetallic system, calcium, iron 2, arsenic 2, and electron dope that in a different way than it has been done before. In particular, it has not been electron doped through the iron site. In other words, if you replace iron with anything this way, you don't get superconductivity for some reason. If we put manganese in there, we get an insulator, and we get a local moment magnet. So it's something drastic changes. So we wanted to do that in a different way, and the only other way essentially is to replace calcium with a trivalent rare earth, and that luckily is possible, so we can put the light rare earths in for calcium. And when we do that, we can grow single crystals, and fortunately we can also play with the flavor of the rare earth, so we can put in lanthanum, cerium, cerium, neodymium, even up to samarium and gadolinium. But there's a limitation in the size of the rare earth. So as we put in smaller and smaller rare earths with the lanthanide contraction, we can put less and less. So here's a plot of the amount of rare earth we put in and the amount that we actually get in the crystal. And so you see when you put neodymium in, you can put up to 40%, but you only get roughly 8 to 10% maximum in the crystal. Whereas if you put lanthanum in, you can put almost 30%, up to 30%. And I'll show you later that if we grow the crystals under pressure, we can put in more just by squeezing the lattice. And we can get up to roughly 50%. So that gives us a nice handle on not only the doping, because this is pure trivalent substitution for divalent calcium. So there's a clear doping going on, and we've established that through Hall measurements and other things. But we can also play with the type of rare earth we put in, and that will control the size of the unit cell. So you can see here that this is the A-axis lattice parameter versus the rare earth concentration. And actually, A-axis doesn't seem to depend much on the type of rare earth. It just increases moderately as we put in more rare earths. But the C-axis lattice parameter actually drastically depends on which rare earth we put in. So lanthanum, you can see, is actually a nice size match for calcium in that the C-axis doesn't change at all, up to almost 30%. Whereas in neodymium, or these smaller rare earths, you can see there's a much stronger change, decrease in the C-axis. And that's just simply understood by the smaller size of the rare earth contracting the lattice using chemical pressure. So that gives us a nice control parameter to use. And in this calcium system, the second interesting feature of the system is that it's very close to a structural instability. So it was actually known before we did this work that if you take calcium iron arsenic, and this is temperature here in C-axis parameter, and you apply a little bit of pressure, it's a moderate amount of pressure, 6 kilobar, you can actually force this material to undergo a severe structural collapse. So the C-axis contracts by roughly 1 angstrom in a very strongly first-order structural transition. And you can see here, so the C-axis goes from roughly 11.5 to 10.5 angstroms very quickly as a function of temperature. So by substituting rare earths, we can actually mimic this behavior chemically rather than applying pressure with an anvil cell or otherwise. And you can see that here, if we put in some praseodymium, we can see this structural collapse. So it's very much like the pressure work. So now we can control that much more carefully using a substitution rather than doing a pressure experiment. And we can actually do a lot more experiments on this particular aspect of the system. This is fairly well understood. In fact, going back to Hoffman's work explaining this, the chemistry of this tetragonal crystal structure, the 122 structure, in the sense that the arsenic-arsenic interlayer distance is a key parameter. So calcium 122 just seems to be very close to this instability where the arsenic atoms want to form a dimer. So in the pure compound with no pressure, they're not dimerized, they're actually not bonded. And if you apply a little bit of pressure, either with an external pressure source or with chemical pressure, you force these guys to form a bond, and the whole tetragonal crystal structure collapses because of that. It just pulls the whole thing. And you can see that through experiment, as I showed. So, and this is, we realize through experiment that this really is the key parameter. So if we take this is X-ray data refined from single crystals. If we take the actual interlayer arsenic-arsenic distance, this distance here, and follow it as a function of temperature, you can see that as soon as we hit this 3 angstrom magic number, it collapses. And if we don't, we can go all the way down, even like these, let's say this 16% cerium dope crystal. We can go all the way down and it never collapses. And so this is a very nice crystal here where you can go to low temperature, and it's very much near this collapse. And we explored that with neutron scattering and using external pressure. So we took this cerium compound here. Here's the C-axis temperature dependence at ambient pressure. And if we apply just a little bit of pressure, you can see the collapse happen at just half a kilobar. So this is, just pushing with your finger, basically, in terms of high pressure work. And so you can show very nicely that this collapse is really controlled by this arsenic distance. So that's well understood. The interesting thing is that if you bring the crystal very close to this instability, you have a huge thermal expansion. You can see here that this is a 0.6 angstroms over room temperature range. And as far as I can tell in the literature, it's the highest thermal expansion, which unfortunately is not very amenable to application. So I'm not rich yet. In terms of the band structure, this is also a very interesting aspect of this collapse, because once you collapse the structure, you can imagine that the bonding changes, the band structure changes dramatically. And it actually does. We can measure through the Hall coefficient a very dramatic change in the electronic structure, where the material becomes almost compensated in this collapsed structure. And this was calculated, and it seems to agree fairly well with calculation. This, in particular, this gamma point band, this whole band, seems to pinch off abruptly. So you go from this 2D, quasi-2D Fermi surface to a very 3D-like Fermi surface. So we're in the process of looking at other materials that are near this instability to see if we can actually probe this Lifshitz transition in some sense, to see if there's some other interesting instabilities that arise from that. But it's hard to really control to get right close to this point. It takes a lot of work to get a composition of the crystal to be right near it. Okay, so in any case, you can take all these different flavors of rare earth and form some phase diagrams. And this is very complicated. I'll actually separate it out by plotting the rare earth composition on this axis and the resultant, the C-axis change in the lattice constant, which is mimicking pressure, basically. If you remember, the A-axis does not depend much on rare earth, so it increases moderately, but the C-axis decreases tremendously. So you can compare lanthanum, which has no C-axis change, so that's just on this axis, pure axis of doping right here, compared to the pure pressure change. It's the pure calcium compound as a function of actual pressure over here. And you can see in between, you can control the variation of doping and pressure together. And so it spans, you see some suppression of magnetism. The interesting thing is that we see traces of superconductivity all around here. In particular, in this range where we see this collapse transition. So that's a provocative result, which I'll explain a little bit more as in the next part of the talk. So the superconductivity is very interesting because it's showing TC values up to 50 Kelvin. So that's what we were really excited about in the beginning. And so there's been not only our group, but several other groups around the world that have reported the same phenomenon, as well as the physical properties. But the interesting thing is that as opposed to seeing the superconductivity in the compound as you suppress the magnetic order, without this collapse business, just looking at the 1-2-2 structure as you suppress the magnetic order like you do in all the other iron pnictides, we see the superconductivity in the collapsed phase. And as I said, that's a very provocative result. And that's provocative particularly because in this collapsed phase, it's thought that the iron moment is quenched. And it's not only thought, but it's actually experimentally proven that the iron moment is completely quenched. And so to have a pairing instability that's caused by magnetic fluctuations, it's very hard to come up with something like that to give you such a high TC in this material that comes about from iron spin fluctuations. So I think I have some. Yeah. So there's some experiments that show that. We did with our collaborators in China some NMR data, which shows that the iron moment really is quenched once you hit this collapsed structural transition. And also with some collaborators in Toronto, Jim Kim's group, with X-ray emission measurements, they can look at the iron moment, the instantaneous iron moment at the atomic level, and see that it actually undergoes this collapse here. So there's a quenching of the iron moment. So how do we get superconductivity in this collapsed phase? That's the real question. Now there's a caveat to that. And the caveat is that the superconductivity we observe in all these compounds is a very low volume fraction. So it's very strange. We see full resistive transitions, as you can see here. But when we measure the magnetic susceptibility, we only see roughly a 10%, effectively 10%, 15% volume fraction of the Meissner effect, of the screening. So there's a transition we can see in the screening. There's screening occurring, but we don't see full screening. And that's very peculiar because, well, I'll get to the phase diagram in a moment, but it's very peculiar because we're doing everything similar to how we do it in all the other iron pnictides. We suppress the long-range magnetic order, we quench it down, aside from the collapse transition business, but we do not get bulk superconductivity. So we've done several tests, and I'll just be blacked out here, but you can trust us that we've tried every kind of permutation of etching and annealing and so on to see if we can either get rid of this superconducting phase or enhance it, and we can't seem to do anything, and there's details in this paper you can see. But the really peculiar thing, which I'll focus on in the last part of the talk, is the fact that this superconducting phase seems to exist separately from the magnetic phase. So unlike the coexistence that I mentioned before in the intermetallic iron nicktides, it seems to exist separately from this, this magnetic phase. So you can see that even just in the resistivity. Here's the pure calcium. This is the magnetic transition here. As you put in lanthanum, you see this gets suppressed down. There's no sign of this high PC phase here, but as soon as you go beyond a certain doping, boom, it comes on and turns on instantaneously. So here's the phase diagram of that lanthanum system, and you can see here that the magnetism is suppressed down, 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 and then we see this high PC phase appear here. There's another parasitic superconducting phase here, but that seems to be independent of all this, and that's kind of another story. You can see that there's this transition here. It's also not a bulk phase, so it seems to always be there, even in the undoped compound. So I'll ignore that for now, and I'll look at this phase, because that's the 50 Kelvin phase, this interesting phase. So the question is there really no coexistence? And this is a chemical substitution. It's hard to really get to this point here, crossover, and study in detail. So what we did was we decided to look at various crystals along this axis and apply pressure. Because pressure, you can tune this system very cleanly, and hopefully, and as I'll show you, we can cleanly go through this phase transition here and see if it's intrinsic or not. So there's 4 experiments involving our own work and 3 other collaborations, and there's nicely summarized here, basically looking at 4 different dopings of lanthanum. So again, there's no collapse business here. This is just lanthanum doping. It's just trivalent for divalent calcium substitution. So there's clamp cell work I'll show you in sequence. Then there's some hydrostatic helium gas cell experiments, neutron scattering and transport, and then some higher pressure anvil cell experiments. So to start, I'll start with our own work, sample S1. So we take a sample that's 10% doped. So here's the magnetic transition somewhere around here. And as we apply pressure, this is in a clamp cell, so it gets smeared out. It's quasi-hydrostatic. It's in a liquid medium that freezes at low temperature. So there's some non-hydrostatic pressure condition. It smears out this transition, but we can follow it. And suddenly, once you cross 10 kilobar, there's an abrupt appearance of this superconducting phase. It's very weak because you can see that the resistive transition isn't even complete, but it's there. And so we can trace out a phase diagram here. We suppress the magnetic order here, and then this superconducting phase appears suddenly here. So this is a nice clean transition. Now 10 kilobar is quite high, and we were afraid that we were getting into the phase where there might be some collapse transition induced. So the next few experiments are involving helium gas. So helium gas so this is the next sample here going down this transition line. Helium gas is quite peculiar because when you apply helium gas or purely hydrostatic pressure to this compound, the suppression of magnetism is about 100 times faster than in quasi-hydrostatic conditions. It's very peculiar, but it has something to do with the anisotropy of the magnetic and crystalline structure and maybe electronic structure. It's unknown, but it's just an experimental fact. Nevertheless, this is a 12% sample. You can see that here's the magnetic transition measured in the susceptibility. Now this is neutron scattering, ambient pressure, just to show you that there's a long-range magnetic order that's observed.
What's this superconducting volume?
Nothing here. This is magnetic. So this is this sample right here. Okay. So now we apply hydrostatic pressure, and this is a neutron scattering experiment, so we cannot measure transport or superconducting properties. But you can see that we can suppress this magnetic order smoothly, and this is measurements of the order parameter as we suppress it to 0 temperature. And you see that by 0.5 kilobar, it's suppressed, as opposed to the last phase diagram I showed you, where it's 10 kilobar. So it's order of magnitude higher to not even suppress this nail temperature. So that's kind of a mystery, actually. And then we also looked at the C-axis just to show you that there's no collapse transition occurring. Up to 4 kilobar, you can see there's basically very little change in the C-axis. So the next experiment is a similar experiment, but actually measuring resistivity under the same pressure range. And it's a slightly higher doped sample, and it's just near this, this transition here. So we were lucky to find a sample that has this, this nail temperature. So here's the resistance versus temperature. Without pressure, you can see there's this minimum here, so the nail temperature is somewhere here. But most important, there's no trace of this high TC phase. Basically, there's no downturn here at all. So there's a downturn here, but that's that parasitic, what we call a 10 Kelvin phase, and that's just always there. But as we apply pressure, and now you can see that the pressure values are very, very small. Basically 20, 50 bar, 50 atmospheres. Right? And we start to see this onset of the high TC phase at 40, 42, 44 Kelvin or so. So this is a very modest amount of pressure, and you can see we can just turn it on very smoothly and actually go back and turn it off. Because it's hydrostatic, we can just go back to zero pressure and come back here. So we try to draw a phase diagram here, but basically there's just an abrupt onset that happens very quickly, and that's because we're so close to this boundary here. So the last sample I'll just show very quickly because not much happens, but the important thing is that TC doesn't actually decrease. It actually goes up a little bit with very high pressure. So now we're looking at 50 kilobar. So that's 1,000 times more pressure than the last experiment I showed you. And TC seems to go up a bit, but it goes down a little bit. It doesn't seem to suppress. So that's quite a high pressure range, and TC is still very stable. So it's very much unlike the other iron pnictides. Okay, and then finally, just to flash it, we actually put up to 40, something like 45% lanthanum using high pressure growth techniques. This is in collaboration with the Canfield group. And you can see that superconductivity actually just persists all the way up. So there's something very different about this phase that does not seem to be some clustering of this is praseodymium in this case, of rare earth, because if you put up to 40%, that's quite a lot more. You're getting here some percolation within. So it doesn't seem to be that case. To sum up the pressure experiments, we can go through this transition very smoothly using pressure, and it seems to be intrinsic in some sense. So really the mystery that remains is that we can suppress the long-range magnetic order, and in every other iron pnictide, when we do that, we see bulk superconductivity. In this case, we don't see bulk superconductivity. But we see this high TC phase that's on order 50 Kelvin. So just finally, to compare to the other phase diagrams that are well known in this iron pnictide system, as I showed before, the oxypnictides, these are all different versions of the oxypnictides. There's a clear, abrupt first order transition between magnetism and superconductivity, where there's some dispute about this, but most people believe that there's no phase coexistence of these two phases in this system, as opposed to the not only the transition metal, but also the alkali earth and the nictogen doped compounds, which show a very clear microscopic phase coexistence. So I'd like to posit that there is some distinction between these two superconducting systems, and perhaps we're seeing some peculiar phase of that in the rare earth doped system that we can actually control in some way. There's lots of questions that remain, including the fact that we see this non-bulk phase to be persistent in all these materials, these rare earth doped materials. And why is the TC so high? Why does it not want to coexist with magnetism? Why does it appear in the collapsed phase, in the uncollapsed phase? These are all the remaining questions. So, thanks very much.
Thank you very much for this inspiring talk. And now it is time for questions.
Okay, so I actually had a couple of comments on the, and maybe questions. So on the collapse thing in calcium, you talked mostly about calcium first. So all our calculations, we find that actually collapse certainly happens, but energetically there's a change in enthalpy. So we call it an enthalpic transition, and in all the 122s, in fact, the calcium, the strontium, the barium, and so on. We also find that actually the orthorhombic magnetic phase remains stable till higher pressure. It's just energetically not favorable. So I guess the name collapse comes from the fact that C-axis decreases, but essentially it's energetically an enthalpy transition. So that was just one comment. But on the other thing that I had was, you didn't show data for barium or the other compounds. Our calculation also shows that we actually associate the collapse tetragonal phase from tetragonal phase to be due to a Lipschitz transition. In barium, strontium, and however, for calcium it's a little tricky. So in calcium we actually find, it sounds funny, but we find the Lipschitz transition at a negative pressure, which means if you sufficiently dope it, you might get it to a positive pressure. So those are the comments. The question was, isn't it true though, as far as the superconductivity and magnetism coexisting? It's true in the calcium case that they don't seem to, but in barium, there seems to be a region where they coexist. Is that true or not?
That's true, but so the whole complication is experimental, practical, because barium and strontium, you require upwards of 10 gigapascals, 100 kilobars, to suppress magnetism and to obtain superconductivity. So there's essentially only transport experiments done to show what, in my opinion, is that they're not coexistent. In fact, you have the collapse phase that comes in, and superconductivity hits once that collapse phase appears. And we have some work on that, actually. We took the calcium system and put roughly 30% strontium in to expand the unit cell a bit and do these experiments. Not only structure and transport, but also X-ray emission. So we have some papers on archive that look at the iron moment and all this stuff and map out the phase diagram. And it's very strange, actually. It seems to be that the iron moment does not, the quenching of the iron moment does not depend completely on the fact that you have a collapse phase or not. It seems to be tied more to the C-axis variation. So I don't know if that...
That's a very interesting comment, because right now, as you say, the experiments say maybe an experimental point, that we see some overlap.
Yeah.
The S3 sample, which you need only a little bit of pressure, but hydrostatic one, can it be replaced by the uniaxial then? So that one could do experiment?
Yeah.
That one?
Yeah, no, definitely. The tricky part is finding a crystal that has that low a nail temperature. Like, we were really lucky to find one, needle in a haystack type of crystal that has that low. So when we try to get, for some reason, we try to pinpoint the doping right around that 13%, we often get nail temperatures of 100 Kelvin, or we're on the other side. It seems to be somewhat unstable, so we haven't sorted out how to really stabilize that doping level. But we're trying to get more. And that's the obvious thing to do, to try to do uniaxial pressure.
And the last question?
So, if I may ask a question, did I understand correctly that whenever you observe a bulk superconductivity, you have a rather small, diamagnetic fraction?
Yeah.
Which means to me that the superconducting cluster to percolate has to be very, very strongly spatially correlated, because otherwise, if you have random, you would not percolate with such a small diamagnetic
That's right.
fraction.
So,
but then the question was, is that under pressure you somehow constrain this superconducting cluster in such a way that it is no longer able to percolate? That is the question.
yeah. So there's some other ideas out there. One is a sort of interfacial superconductivity mechanism, which is proposed by the Houston group. Or just more naively, just some clustering where you have some essentially impurity phases, right? So that's essentially why we did this set of experiments, to try to see if we cannot turn on and off this phase with pressure, which is very clean, and low pressure, very, very low pressure, where we're not changing anything about the crystals. The energetics are very, very low. So in my opinion, when we apply 50 bar of pressure, no atoms are moving. We're low temperature, we're at very low pressures. So when you see the onset of that thing, to me, it's intrinsic, but it's very peculiar, because it's obviously not bulk. So we don't know what it is. We're in the process now of doing TEM experiments to see if there is some superstructure that may be responsible. Maybe the energetics are very low for that. It's extremely low, but maybe that's the case.
Thank you.
So, thanks the speaker again.